Up to this point, we've been talking only about integers, and now we're going to talk about another set of numbers called rational numbers. And the set of rational numbers is so vast that we can't list all of its members, even using this roster method with a ... But we describe rational numbers like this. They are all of the numbers in the world that can be written in the form a over b, where a and b are integers and b is not equal to 0. Now, b can't be equal to 0 because we can't divide by 0, as we saw a little bit ago. Well, what kinds of numbers are these then? What numbers can be put into this kind of form? Well, certainly a number like 2/3 is in the form of a rational number, so 2/3 is a rational number. -4/7 is a rational number. 5 is a rational number because it can be written in the form a over b. That is, it can be written in the form 5/1, and therefore it is a rational number. So every integer that we have discussed before is also a rational number. You see, all the integers fall into that set, and there are many other numbers that are in that set as well that are not integers. 7/10 is a rational number because 7/10 can be written in fractional form as 7/10. Now you're recognizing here that the rational number, the world of rational numbers, is really the world of fractions. And that's a real good way to look at it, that when the word rational number is used in a textbook or in some instructions, the idea of fractions should come to mind. Now, when fractions come to mind, decimals follow very shortly, don't they? After all, decimal numbers, terminating decimals like this one, decimals that have a fixed number of digits, are rational numbers. They can be put into the rational number form. Let's talk about conversion between decimals and fractions. Now, going from the decimal form to the fractional form is really easy. Like in this case, this decimal becomes this fraction, and all we have to do is read the decimal and write it down as a fraction. If we read this correctly, we read it as 7/10, and we write down 7/10 as a fraction, and we have converted from the decimal form to the fractional form. Well, going from the fraction form to the decimal form is not quite as obvious. Although we have a clue about what we might do to change 5/8 into a decimal from our experience before. We know that when we were dividing integers, this can be thought of as an integer division problem, you see. So every fraction is an implied division problem, and if we just go through that idea of division, we can change this into a decimal. So this is 5 divided by 8. So we would do this. We would say 8 into 5. Now 8 doesn't go into 5, so we'll have to add a decimal and some zeros to continue the division process. And the decimal, you know, goes straight up into the answer, and we say 8 into 50 goes 06. 6 times 8, 48. Draw the line, subtract, we get 2. Bring down the next digit. 8 into 20 goes 2. 2 times 8, 16. Subtract 4. Bring down the next digit. 0. 8 into 40 goes 5. 5 times 8, 40. The division goes evenly. We are finished. The answer is 0.625, or 0.625. Often you'll see the 0 to the left of decimals as the proper way to write this in decimal form. Well, a number like, or a rational number, or a number in purely rational form, as 4/9 can be changed into a decimal like this. It's 4 divided by 9, or 9 into 4. Now notice the division. The division is 9 into 40, goes 4 times. 4 times 9, 36. Subtract, we get 4. Bring down the 0. Gee, we had a 40 up here, we have a 40 right here. It's going to do the same thing, you see. So the division turns out to be 0.44444444 forevermore. The ... means and so on in this pattern. So this 4 is repeating. And there is a clever way to indicate repeating decimals like this, and it's by using a bar over the digit or digits that repeat. Here the 4 is repeating, so I would write the bar over the 4, and that indicates a repeating decimal. Here we have 4 divided by 11, and again we'll get a repeating decimal, but this time 2 digits repeat. So it's 11 into 4.0000. 11 into 40 goes 3. 3 times 11, 33. Subtract, we get 7. Bring down the 0. 11 into 70 goes 6. 6 times 11, 66. Subtract, we get 4. Now this 4 with the 0 that's brought down starts the whole process over again. So we're going to get 3. 3 times 11, 33. Subtract, we get 7 as we did before, and so on. So this situation is repetitive, and it's 2 digits that are repeating. And to show that 2 digits repeat, we'll use the same technique as before, putting a bar over the 2 digits that repeat. This bar, incidentally, is called a vinculum, I think. To add and subtract rational numbers when they are in fractional form like this, we just follow all of the rules for fractions that we know in the past, and then we consider the sign idea. Now, thinking about 5/6 and 3/10, you know, when we're adding and subtracting fractions, we understand that fractions are composed of numerators and denominators. The top number is the numerator, the bottom number is the denominator. The numerator tells how many things we have. The denominator tells how big those things are. So for the fraction 5/6, just ignore the sign for a moment. For 5/6, we have 5 items, and each one of them is a sixth. And here we have 3 items, and each one of those is a tenth. And in order to bring fractions together, they have to be of the same size. And we have to be describing the same sized items. So we need a common denominator. Now, to find a common denominator, we need the least common multiple. The common denominator is the least common multiple for 10 and 6. And there are a couple of ways of finding that least common multiple. One way is to just choose the larger of the two and just consider multiples of that. And when you hit upon one that the other one will go into, like here, multiples of 10 would be 10 times 1, 10 times 2, 10 times 3, 10 times 4, and so on. So it'd be 10, 20, 30, 40, 50, 60, etc. And so you would just start with 10. Does 6 go into 10? No. 20. Does 6 go into 20? No. 30. Does 6 go into 30? Yes. You see, 30 turns out to be the least common multiple or the common denominator. Another approach to take with finding the least common multiple or the common denominator is to go through a process called prime factorization. Now, so to find the least common multiple, we perform this idea of prime factorization. Now, the word prime, there are prime numbers and composite numbers. Prime numbers are numbers that can be written only as 1 times itself. They have no other factors within them other than 1 and itself. 7, for example, is prime. It can't be written in any other way as a product other than 1 times 7. Now, 6, on the other hand, is not prime because 6 can be written not only as 1 times 6, but also as 2 times 3. So 6 is not a prime number. At any rate, we want to write the number that we're talking about, these denominators, as a product of prime numbers. So that's what prime factorization refers to. 6 is written as 2 times 3. 2 is prime, 3 is prime, you see. A prime factorization, prime factors. All right, 10 is 2 times 5. 2 is prime, 5 is prime. Now, once we have the prime factorization forms of our 2 denominators, we can find our least common multiple by using every one of the factors that we see up here. So the least common multiple contains every different factor that we see. We see a 2 factor, we see a 3 factor, we see a 5 factor. Now 2 appears up here, 2 appears down here. We don't list it twice. We list it we list every different factor that we see in either one of these prime factorizations. So it's 2 times 3 times 5. Let's see, 2 times 3, 6, 6 times 5, 30. Oh, it's 30 as we expected from before. The prime factorization idea comes in handy when the denominators get unreasonably large. If they're pretty big numbers, then the prime factorization method works pretty well. Well, that's the gist. There are some other nuances involved in the prime factorization method, but that's the basic idea. All right, so 30 is the common denominator, and when we change into that common denominator, then we go through a process kind of like this. It is, let's see, 6 into 30 goes 5. 5 times 5, 25. And 10 into 30 goes 3. 3 times 3 is 9. Now that's one way to do it. That's the way you probably learned in grade school. Another way is like this, where we're thinking, gee, if we're going to change into so many 30ths here, what do we need to multiply 6 times in order to get 30. 6 goes into 35 times. So we're multiplying this by 5. That means we have to multiply that by 5. So fundamentally, we're multiplying this fraction by 5 over 5. You see, and 5 over 5 is a form of 1. When you multiply something by 1, you're not changing its value, you are changing its form. And that's all we're doing here, changing the form of this fraction, but not its value. We want its form to have a denominator of 30, you see. So that's the idea. At any rate, we're multiplying by 5 over 5, and that, again, gives us the 25 over 30 as expected. The little routine of 6 into 30 goes 5, 5 times 5, 25, accomplishes this very quickly. Okay, at any rate, we have common denominators, and when we have common denominators, we know from our past experience that we collect numerators. And in this kind of environment, it's probably wise to burn a step and write something like this. Write the two numerators. That we're now ready to collect numerators. And so it's wise to write this as negative 25, you see, plus 9, both over 30, or entirely over 30. And now, 25 plus, negative 25 plus 9, signs are different. So take the 9 from 25, we get 16, and attach the sign of the larger one, so it's negative. So negative 16 over 30, which we reduce to 8 over 15, negative 8 over 15. Now, there is something else. Let me spread this out just a little bit so you can see it more clearly. Negative 8 over 15. Something else I think we ought to talk about right here is, notice that this sign appears in this numerator right here as I've written it. Actually, there are 3 signs within any fraction. You can think of any fraction having 3 signs. There is in the fraction 2/3, there is a sign of the numerator. It's understood to be positive here. This is a positive 2. There's a sign of the denominator, and there's a sign of the fraction itself. And just for 2/3, they're all considered to be positive or plus. Now, in the process of moving signs around, you can think of the manipulation of the sign of a fraction like this. You can think of, okay, I can change any 2 signs. I can change any 2 of those 3. For example, in 2/3, this is plus 2 over plus 3. If it's minus 2 over minus 3, it has the same value, you see. Negative divided by negative would be positive. So this is equivalent to the 2/3. I have changed 2 of the signs. So you can change any 2 signs in a fraction and be safe. Now, another way, something that more often happens is that you have a minus sign somewhere in the fraction, like here. And you would like to write the sign of the entire fraction. You're more interested in that than having the sign of a numerator and the sign of a denominator. So although you understand that there's a plus sign here and a plus sign here, you can change these 2 signs, you see, and make this negative and that positive, and then you don't write the plus signs. All right? Or you can just say that a minus sign can float to any of the 3 positions. You can write the minus sign here, or as the sign of the fraction, or as the sign of the denominator, as the need arises. Now here, I'm just taking this minus sign and I'm letting it float to the position of the sign of the fraction. I think that's the easiest way to look at the situation. Well, let's consider another one. Here we have negative 3/4 plus 1/6 minus 5/8. Don't pay any attention to the signs to begin with. Let's just find a common denominator. And I think the technique of just saying what's the smallest number that all 3 of these will go into a whole number of times is a pretty good technique. And we could, to discover that smallest number that all 3 of those go into a whole number of times, we can think about multiples of the largest of these 3, the multiples of 8, as prime candidates for our common denominator, or least common multiple. So let's see, multiples of 8. 8 times 1 is 8. Does 6 go into 8? No. 8 times 2, 16. Does 4 go into 16? Yes. Does 6 go into 16? No. So we discard 16. All right, 8 times 3, that's 24. Does 4 go into 24? Go like this. Does 6 go into 24? Oh, happy day. All 3 of them go into 24. So we have our common denominator, and away we go. So we write this. And notice that I'm going to park a sign in front of these fraction bars, and I'm going to pop in the common denominator, and then I'll go through the process of making the change. And I'm thinking through, you may notice that as I discuss a problem like this, I'm trying to think through it the way that I would like for you to think through it. And I'm writing what I think that you ought to be writing. And so from that, I'm hoping that you're learning this process of thought. Now, you'll go through the thought process a lot faster later on when you have a little more experience with these things than I do here, but this is basically the way that you want to proceed through. Okay, so we go 4 into 24, 6. 6 times 3, 18. And then 6 into 24, 4. 4 times 1, 4. And then 8 into 24, 3. 3 times 5, 15. And now we'll write this as one great big fraction with 24 as the denominator. You see, so it's that now. I'm going to move this minus sign to the numerator, so it'll be negative 18, or minus 18, plus 4, then minus 15. And all I have to do now is collect in the numerator. So let's see, I've got two negatives, and it's pretty easy for me to add the digits involved in those two. So that would be 33. So it'd be negative 33. I'll write another step just to show that. Typically, you might not do this, but just for emphasis, I'm going to. Negative 33, then plus 4 is what I have next over 24. And then this is equal to, let's see, negative 33 with plus 4. The signs are different, so I'm going to subtract. I take 4 from 33 and get 29. So I get 29, and it takes the sign of the larger of these two, which is negative. So negative 29 over 24. And then I would probably move this minus sign to be the sign of the fraction. Although it's not wrong to leave it like this, it's just a little more, well, it's not more correct. It's from a form standpoint, this is just a little bit better as an answer. This would more likely be the answer in the back of the text, perhaps, than that would. Here we're adding rational numbers that are in the decimal form. And when we add or subtract in the decimal form, the key is to line up the decimal points. That we're actually going to work the problem vertically. But to work it vertically, we line up the decimal points, and we do that like this. Now I'm writing 14.02, and then I want to add 137.6. So I'm adjusting the digits so that the decimal points line up. So I want 137.6 like this. I also want to call your attention to the idea and emphasize that when you work problems like this, that especially with decimals, that you want the digits of the same value to line up vertically, and to be able to see them more clearly, you want to write a little bit larger. Just write a little bit bigger and concentrate on lining the digits. Like here, where I'm trying to line these up, and so on. And then the 9.852, that's 9.852. Giving a little more separation between digits here than I did up there, you see, to try to emphasize what I'm adding once I get to the adding step. So I'm just adding straight up and down here. And working from over here, it would be okay to fill these vacant positions with zeros as placeholders. That's okay to do. If you want to do that, I'll just dot them in here a little bit. But we need to be able to see that there's nothing here to be added to the 2. So we just have 2. Once we add 5 and 0 and 2 is 7. And then 8 and 6, 14. I get 4. Bring down the decimal. I get a 4, but I have 1 to carry. So 1 and 4, 5. 5 and 7, 12. 12 and 9, 21. Bring down the 1, carry the 2. 2 and 1, 3, and 3, 6. And then bring down the 1. So 161 and 472 thousandths. Notice how I read that? 161 and 472 thousandths. Here we have a situation where the signs are different. And we have to consider this sign situation when we're dealing with rational numbers. And although we want to arrange our problem so that the decimals are up and down from one another so we can do the adding or subtracting, we have to really think about how this is going to work out, because we've got a minus and a plus. The signs are different, so we're going to subtract. And our order of business calls for us to take the smaller digits from the larger digits. Well, as a number without regard to sign, that's a bigger number than that one is. So we're really taking this from that, you see. And then we're going to attach the sign of the larger one, you see. So our answer is going to be negative. But when we actually go through the process right here, we're setting it up to where we're taking 84.76 away from 114.039. You see, so we're setting it up like this, and then we get our difference between these two, but the sign of this should be negative. So although we perform this as a subtraction, we attach a minus sign here, and the answer is negative 29 and 279 thousandths. Recall that when you multiply fractions, you fundamentally multiply straight across. You multiply numerators times numerators and denominators times denominators. And a nice shortcut here, save a little time sometimes, you look for cancellation opportunities. Well, here, if we're multiplying straight across and we do not take advantage of the cancellation opportunity, then it would be 7 times 9, 63. And it would be 12 times 14, which is 168. And negative times positive is negative. And then we would have to reduce this. We would have to reduce it. Well, that means we could divide it, I think, by 3. Actually, I think there's a larger number that would go into both numerator and denominator. But wow, it seems like a big project, doesn't it? Well, let's go through the project anyway. I see that 3 will divide the numerator, and I can use a divisibility test in the denominator. Let's see, 8 and 1, 9, 9 and 6, 15. 3 goes into 15, so 3 goes into that number. So 3 will divide both numerator and denominator. 3 into 6 goes 2, 3 into 3, 1. Let's see, 3 into 16 goes 5 with 1 left over. 3 into 18 goes 6. And let's see, I think maybe 7 goes into both numerator and denominator at this point. 7 into 21 goes 3. 7 into 56 goes 8. So we get negative 3/8. Now, this is what happens a lot of times when you don't take advantage of cancellation opportunities. You get into a mess where you've got to go through a lot of this reduction of the fraction at the end of the problem. It's a little easier, because you're dealing with smaller numbers, to look for the cancellation opportunities. And here we see a couple of them. The 9 and the 12. 3 into 9 goes 3 times. 3 into 12 goes 4. And the 7 and the 14 also, we have a cancellation opportunity. So 7 into 7, 1. 7 into 14, 2. And now multiplying straight across, 1 times 3, 3. And then 4 times 2, 8 for the denominator. And don't forget about the sign. So negative 3/8 for the answer. A lot easier than going through this process. Division of fractions involves changing to a multiplication problem. Remember, when we see the division of fractions, we multiply by the reciprocal. So we go through the process of rewriting as a multiplication problem. So this becomes 3/10. Change the sign to times. Now it's almost redundant to use a dot here and a parenthesis. I could just use a parenthesis, but for emphasis, I'm changing the symbol, the operation symbol, to multiplication, and I'm going to multiply by the reciprocal. I'm just flipping this fraction over, so it's negative 25 over 18. And once again, we don't have to have both the dot and the parenthesis, but let's leave them there for now. We're looking for cancellation opportunities, and we do indeed see some. We have the 3 and the 18. 3 into 3 goes 1. 3 into 18 goes 6. And then 5 divides both the 10 and the 25. 5 into 10 goes 2. 5 into 25, 5. Now, multiplying straight across, 1 times 5, 5. 2 times 6, 12. So we get 5/12. But don't forget about the sign situation. We have one of these factors is positive and one is negative. So we have unlike signs and therefore a negative result, negative 5/12. Do notice, though, how I thought about finding the number part of the answer and the sign part of the answer sort of as two separate events. And that helps to keep things organized. In my mind, it does anyway. All right, here we're talking about rational numbers in a decimal form, and we're multiplying. And remember, in this situation, we really don't care about arranging decimal points up and down from one another in some kind of column. that doesn't make any difference. All we're doing is just writing digits so that they are kind of right justified. So we're looking at columns kind of like this. And now we multiply as we normally would, and we'll place the decimal later. We'll also place the sign of the answer a little bit later as well. But 8 times 4 is 32. I'm carrying 3. 8 times 4 is 32, and 3 is 35. Carry 3. 8 times 5 is 40, and 3, 43. And now 3 times 4, 12. And remember that first digit goes under the 3 here. So 3 times 4, 12. I'm carrying 1. 3 times 4, 12, and 1, 13. Carry 1. 3 times 5, 15, and 1, 16. And now I draw the line and add digits. And here's where it's important to have the digits in line with one another or in columns. So 2 and nothing is 2. 5 and 2, 7. 3 and 3, 6. 6 and 4, 10. Put down the 0, carry the 1. 1 and 1, 2. Now to place the decimal in the answer, we count the number of digits that fall to the right of these decimals. And we have to have the same total number of digits to the right of the decimal in the answer. So up here we count 1, 2, 3. There are 3 digits to the right of the decimals up here, so there needs to be 3 digits to the right of the decimal in the answer. So we count from over here, 1, 2, 3, and now we have 3 digits that lie to the right, so 20.672. Now let's not forget about the sign situation. Now some people will write the answer right here, leave it right there, and just put, because we have a positive and a negative that are being multiplied, just put the negative sign right here and be done with it. Other people will want to write the answer in a different position as negative 20.672. Here's another one. It's a division problem involving decimals. And you may recall from arithmetic that all we do is set up the long division for the two numbers, and then we go through a little routine to place the decimal in the answer. It kind of looks like this. We have this number divided by that one. This is our divisor, so we start with that in setting up the problem. It's 1.7 then into 0.394. Now notice that I didn't write the negative sign here. I'm going to consider the sign right before I write the answer, or after I have written the answer. I'll either attach a negative sign or not, and it looks like I'm dividing a negative number by a positive number. Signs are different, so I'll get a negative result. Now I can put that up here right now if I want to. You can consider it right now and dispense with it so that you won't forget it later, or not, or you can put it in a little while later. Let's put it in later. This kind of follows what we are more accustomed to from arithmetic. So 1.7 into this decimal, recall that we go through a little routine to place the decimal in the answer, and that routine is this. We say, well, we can't divide by anything but whole numbers, so to make this into a whole number, we move the decimal one place to the right. If this decimal point moves one place to the right, then that decimal point needs to move one place to the right, and then it moves straight up into the answer. So now we've placed the decimal into the answer even before we start to divide. So we say 17 into 3. Gee, that doesn't go. 17 into 39, that goes 2 times. So 2 times 17 is 34. And then draw the line and subtract. We get 5. Bring down the next digit. 17 into 54 goes 3 times. 3 times 7, 21. Carry 2. 3 times 1, 3, and 2, 5. Subtract, we get 3. And now if we want to continue the division process, that's easy enough to do. We just tack on a 0 or 2 or 3 or 4 or however far we want to go and continue to divide. Now if I add another 0, I bring it down here and I say 17 goes into 30 one time. 1 times 17 is 17. Subtract, I get 13. And then I could bring down another 0 and continue. Now in continuing here, I would be looking for the place where digits begin to repeat. But that repetition may not occur until I am beyond the accuracy that I need in my problem. You see, I may only need accuracy in this problem up to the hundredths digit. So if I'm going to round off to the nearest hundredths, then I would carry the division out to the thousandths place, one digit beyond where I want to round off. And the reason to carry it out one more digit is so that you can look at that next digit. And here we have carried the division out to the thousandths place. And if we're rounding off to the hundredths, here's the hundredths digit. We're rounding off to this digit. We look at the next digit and recall that the rule is that if this digit is below 5, then we just lop it off. If it's 5 or bigger than 5, then we'll add 1 to the hundredths digit. Okay, it's below 5, we'll lop it off. So our answer is going to be 23 hundredths. And we might write that answer like this. It's approximately equal to, that's what this means, approximately equal to, and it's negative, remember from above, 0.23. So this division is approximately negative 23 hundredths. In this chapter, we have talked about a number of sets of numbers, several sets of numbers. We started our whole discussion in this chapter with natural numbers, the set of natural numbers. And we talked about the set of whole numbers, a set of integers, set of rational numbers, and it's kind of important the way that those sets relate to one another, and I want to talk to you about that just a little bit. There are other sets of numbers that we need to discuss as well. Beyond the rational numbers, doesn't seem like there are any other kinds of numbers in the world, but remember, rational numbers were numbers that can be put into the form of a over b, and as decimals, those numbers turned out to be either non-repeating decimals, either decimals that have a last digit, or as a repeating decimal. But isn't there such a thing, or could there be such a thing as a non-ending and non-repeating decimal? Yes, there could be, and they would then fall into a category that's outside of rational numbers. Well, that's what irrational numbers are all about, and the rationals and irrationals together give us a set called real numbers. Well, here's a discussion of the whole thing and how all of these sets relate to one another. A set is simply a collection of objects or things. We'll be talking about sets of numbers. Now, sets of numbers are often designated like this. Notice the symbols on either side of this listing of numbers. These are called braces, and the braces are just used to contain the items that are listed within a set. So this set A contains the items 1, 2, 3, 4, and 5. The notion of subset is related to the idea of set. Suppose we list another set B, and B consists of the elements 2, 3, and 4. Notice that 2, 3, and 4 are all elements that are contained within set A. And because of this kind of arrangement, set B is said to be a subset of set A. Now, we mentioned the notion of subset because we're going to be building our idea of the real number system with subsets, and we'll start with the natural numbers. Now, natural numbers are composed of numbers 1, 2, 3, and so on. The ... means and so on in the pattern that has been established. Now, natural numbers are also sometimes referred to as positive integers. Well, when 0 is attached to the set of natural numbers, we have a new set of numbers called whole numbers. The whole numbers consist of 0, 1, 2, 3, and so on. Now notice that all of the natural numbers are contained within the whole number, so natural numbers represent a subset of the set of whole numbers. Now, whole numbers are sometimes also referred to as non-negative integers. But when the negative integers are put together with the whole numbers, we get the set of integers. The integers are composed of positive numbers, negative numbers, and 0. Now 0 itself, by the way, is neither positive nor negative. When the set of integers is combined with fractions, now this is just everything that we understand as being fractions, just common, ordinary, everyday household fractions, we get a new set called rational numbers. The set of rational numbers is so extensive that we can't really list the items within the set. We can symbolize or represent them, though, with A over B. Now, all the numbers in the world that can be written in the form A over B, where A and B are integers, are rational numbers. Also included in this definition is the notion that B cannot be equal to 0, an idea that we'll talk about later. Now, what numbers are rational numbers? Let's list a few. Now, think about all the numbers that can be written in the form A over B. Well, common fractions like 2/3 are in that form, so those are rational numbers. A number like 7 and other whole numbers can be written in this form also by just thinking of them as being over 1. You see, we can write 7 as 7 over 1, the form of a rational number. Mixed numbers like 3½ can be written as improper fractions. We would say 2 times 3 is 6, 6 plus 1 is 7, so 7 over 2 is equivalent to 3½, the form of a rational number. So all mixed numbers are a part of this set. Now, what about decimals? Well, consider a terminating decimal, that is, a decimal that has a last rightmost digit, 4.25. Now, if we just say the decimal in proper form, that is, we say this as 4 and 25/100ths, we are mentioning a mixed number, and therefore we are mentioning an improper fraction, the form of a rational number. So all of these terminating decimals turn out to be rational numbers. Now, other kinds of decimals, repeating decimals, are also rational. This is 1.33333 and so on. The little bar above the 3 means that the 3 repeats infinitely far. Now, this is equivalent to 1 1/3, which again can be written as an improper fraction. Now, what we're seeing here is that regular fractions, whole numbers, the negatives of whole numbers, that is, negative integers, mixed numbers, terminating decimals, and repeating decimals can all be written in the form of a rational number, that is, in the form of a over b. So they're all rational numbers. Now we might be thinking, what other numbers are there to be contained within the set of real numbers? Well, there's a rather substantial set called irrational numbers that are not part of the rational numbers. Now, irrational numbers are simply decimals that are non-ending and non-repeating. What items would be in this set? Well, probably the most well-known item is the item pi, a never-ending, never-repeating decimal. Also, the square root of numbers that are not squares turn out to be irrational numbers, and we'll talk about the square roots of non-squares at a later time. Well, the irrational numbers, along with rational numbers, together make the grand set of real numbers. Now, real numbers are often illustrated by using a number line. Now, the important thing about a number line is that it starts at 0, and that number is called the origin of the real numbers. And from 0, if we look out to the right, we see positive numbers, and to the left of 0, we see negative numbers. Now, 0 itself, remember, is neither positive nor negative. Now, what we've done here is we've labeled the 1, 2, 3, 4 to the right of 0, and -1, -2, -3, -4, and so on to the left of 0. But really, the real numbers contain all the numbers in between those integers that we have listed. Now, a notion related to this number line idea is the notion of taking a number like -1.25. Take a number and then find its location on the real number line. And in finding the location and marking it, we are plotting that point. Another idea is that given a point on the real number line, like this point, and calling it by name or naming its position is really naming the coordinate for that point. And the plotting or graphing of points and naming coordinates of points on the number line brings up a rather interesting relationship. And that is that given any real number, we can locate a point on the number line, on the real number line, to describe that point. And on the other hand, every point on the real number line has some real number associated with it. Well, in our discussion of real numbers, we have developed a number of subsets. We talked about these important sets along the way: natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. Now, let's talk about the relationship between them. We know that several of these sets are directly related. That is, we talked about natural numbers, whole numbers, integers, and rationals as having a particular relationship. We have this subset relationship among these various sets. Now, to put this all in perspective, think about this box as containing all of the real numbers. Now, real numbers are composed of rational numbers and irrational numbers, and those two sets have no members in common. The rational numbers, however, have a number of important subsets involved with it. First of all, we might think of the integers as being part of the rational numbers, but the integers have whole numbers as part of that set, and whole numbers are composed of natural numbers. So here's how all of these sets are sort of related to one another. And we should be able to take a listing of numbers and place them into one or more of these various sets. A discussion of exponents can begin with a discussion of addition and multiplication. Here, for example, we see that 5 is added 4 times, and we know that we say that this is 4 times 5, and we indicate it as 4 times 5 like this. Well, in a similar way, we can indicate repeated multiplication. Now here, notice what we have, that 3 is used as a factor 4 times. We have 4 factors of 3. Now that situation can be indicated like this, with a 3 and a little raised 4. The 3 is referred to as the base in this situation, and the 4 is referred to as the exponent. Now the exponent simply indicates the number of times that the base is used as a factor. That's all it's telling us. We read this as 3 to the 4th power. The word power refers to the exponent. Here we have 5 factors of 7. To indicate 5 factors of 7, we use 7 as a base and 5 as the exponent. Now we read this as 7 to the 5th power. One of the most commonly made errors involving exponents is this one. Look at negative 5 squared written like this with parenthesis and negative 5 squared written like this without the parenthesis. These mean two entirely different things. You see, the base of this exponent is negative 5, and the base of this exponent is only the 5. So this means negative 5 times negative 5, or 25. And we don't really have to write this step if we understand that this is negative 5 times negative 5. We could go directly to the answer. But this means negative 5 squared. That is, only the 5 is squared here. It's negative 5 times 5, or negative 25. So something to be very careful about. If it were intended in this problem that the negative was part of the squaring process, then the parenthesis would have been used to enclose that negative sign, or include it with the 5. Here we have negative 2 to the 3rd power. This, we're going to look at the situation again. Sometimes the situation doesn't make any difference. That is, it kind of comes out in the wash either way, and this is an example of that. Negative 2 cubed means that we have 3 factors of negative 2. So this means negative 2 times negative 2 times negative 2. Now, we have 3 factors that are negative, so the answer is going to be negative 2 times 2, 4 times 2, 8. So negative 8. And here, this is negative 2 cubed, negative, and then 3 factors of 2. So 2 times 2 times 2. So any way you cook this up, we get negative 8. 1 as the base of an exponent, or negative 1, represents a rather interesting situation. 1 to any exponent is going to end up being 1, because no matter how many factors of 1 we have, we're going to get 1 as the product of that string of factors. So this is simply 1. Now, negative 1 as a base, the answer in this situation depends upon the number of factors of negative 1 we have. You see, if we have 20 factors of negative 1, we have 20 negative factors, then they can be paired up, you know, as that pairing, we saw that pairing earlier. So if we have an even number of negative factors, we're going to get a positive result. So this is going to be 1. But if there are an odd number of negative factors, then it's like they'll all pair up except 1, and so we'll get a negative result for our product. So negative 1 is the answer here. When fractions are raised to exponents, it's important to know that we can look at the situation in 2 different ways. And it's important to know that because there will be circumstances where we're going to have to use one technique or the other. Here, for example, we can think of this as being, as 3/5 as being the base of the exponent, and it is indeed. But so we can attack the problem by saying this is 3/5 times 3/5, and then multiplying, we get 9 over 25. Now, another way to view the problem is like this. We're squaring 3/5, sure, but notice that we have 2 factors of 3, or 3 squared, and we also have 2 factors of 5, or 5 squared. So another way, an equivalent way to think from this step is that we are squaring both the numerator and denominator. So we can think of squaring them separately and think of the problem like this. In either event, we get the same answer. But sometimes it's important to think about the problem this way, sometimes like this, for manipulation purposes. Here we have negative 2/3 cubed, which means we have 3 factors of negative 2/3. And once again, it's the same idea that we had before. And this minus sign can be thought of, we can float the minus sign if we want to. We can leave this minus sign as the sign of the fraction. One technique that could be used here is to float the negative sign up to the numerator and say this is negative 2 cubed over 3 cubed. That's a technique which allows us to think about numbers, just regular integers raised to exponents, rather than the entire fraction all at one time. So you're thinking of it like this and trying to think of 3 factors of negative 2/3 is a lot to keep track of. This is a little bit less to keep track of and will give us an answer of, well, let's see, 3 factors of a negative, that's a negative result. 2 cubed is 8, so it's negative 8 over 3 cubed. 3 times 3, 9 times 3, 27. So negative 8 over 27, or the negative of 8/27. So if we float that minus sign back to the sign of the fraction. Take a look at this pattern. I've written some numbers over here in this column, and over here I have taken those numbers and I have squared those numbers. I've written an exponent 2 on them, and so it means that we have 2 factors of these numbers. And the result of squaring gives us a number which is called a square. So 3 squared is 9. 9 is the square of 3. All right, that's the terminology that we're going to become familiar with. All right, 1 squared is 1, 2 squared 4, 3 squared 9. We also notice that negative 3, when squared, 2 factors of negative 3 also gives 9. So 9 is the square of both 3 and negative 3, because when both 3 and negative 3 are squared, we get 9. And in that sense, 16 is the square of both plus and minus 4, because plus or minus 4 squared is 16. Plus or minus 5 squared is 25, and so on. All right, now, we're going to work this in reverse, as I say. That is, we want to be able to take a square, or we want to create a name and a process for taking a square and identifying the numbers that are squared to get that square. What numbers were squared to get that square, you see? And we can see here that if we're starting with a square that's 9, that the number squared to get that 9 is either 3 or negative 3. Now the request for the number which, when squared, gives this square is called square root. So in kind of working this in the opposite direction, taking a square and requesting the number which, when squared, gives that square, is the idea of square root. So in terms of terminology, these numbers are square roots of those squares. Square roots. Now we notice that the squares actually have 2 numbers that can be squared to get them, and therefore there are 2 square roots of each of these. The 2 square roots of 9 are 3 and negative 3. The 2 square roots of 16 are plus and minus 4. The 2 square roots of 25 are plus and minus 5. So if we were asked to answer the question, or to produce the square roots of 81, then we could do that by saying, what numbers, when squared, give 81? Well, certainly 9 squared, or 9 times 9 is 81. So one of the square roots is 9, and the other is negative 9. Now, to make the request for square root, rather than writing a phrase something like this, we have a symbol, and that symbol is called a radical sign. Now, here's the request for one of the square roots of 25. And we know every square has 2 square roots. This is the request for one of them. And we read this, the square root of 25. This symbol is called a radical sign. The number under the radical sign is called a radicand. And the radical sign along with the radicand, this whole business right here, is called a radical. All right, now this is the request for the positive square root of 25, often referred to as the principal square root of 25. So the square root of 25 is 5. Now when I say the square root of 25, You see, requested like this, there's only one when we're requesting the principal square root of 25, although there are two square roots of 25. It's kind of a point of confusion. It's thought that when we say the square root of a number, you see, that it implies that there's only one square root of a number. And certainly when the request is made like this, that's true because we are requesting one of the square roots, and it is the one that's the principal square root. If we want the other square root, it's requested this way. The negative of the square root of 25, or the non-principal square root of 25. Kind of works out nicely, doesn't it, with our idea of positives and negatives, because we can just think of this as the negative of the principal square root of 25, and that's negative 5. Okay, so that's the whole idea. The square root of 49, let's see, that principal square root of 49, that would be 7. The negative of the square root of 1, or the non-principal square root of 1, you see. And I think the best way to think about this is that square root, that using that symbol, that square root symbol, the radical sign, we're always going to get a positive result, you see. And so just kind of ignore the sign right here. The square root of 1 is 1, and this is negative that value. So this is negative 1. Negative square root of 36 is negative 6, because the square root of 36 gives the 6. Now, there's a big difference between having a minus sign out here to the left of the radical sign and having a negative sign inside of the radical, or as part of the radicand. The square root of negative 16 would be a request for a number which, when squared, gives negative 16. That is, what number times itself is negative 16? Is there any such number we can multiply times itself to get negative 16? No. So, because there is no such number, we say that there is no real number that fills this bill. Now, I will tell you this, that there is a number within a system of numbers that is the square root of negative values. But we just haven't encountered that set of numbers yet. So for the time being, we'll just say no real number here. Now, the request for square root and the calculation of square root can be made on calculators. And certainly, we can take the square root, or we can estimate the square roots of numbers that are not squares. That is, we can estimate the square root of a number like 5. And it is a request for a value which, when squared or multiplied times itself, gives 5. That is, what number times itself is 5? You see, that's what this is saying. And we make the request on the calculator like this. Now, with graphing calculators, it's done by accessing the square root symbol. And on the TI-83, it's a second function. It's the second function on x squared. And on many calculators, it's that way, as a matter of fact. So we press this button and then enter the 5 and then press enter, and then it makes the calculation, and here's what I get on my calculator. So this number times itself will give approximately 5. Now, I say approximately because when we take the square roots of numbers that are not squares, we get values that are never ending and never repeating decimals. That is, we get irrational numbers. So the best we can do with this is have an approximation for this square root, and that's what this is. It's a very close approximation, but it is only an approximation. Now, on scientific calculators, the request is made a little bit differently. It's not made in this order. We actually enter the number that we want to take the square root of, and then we press the button that has square root involved in it. And on one scientific calculator that I have, that button is marked square root of x. So we press the button marked this way. And on scientific calculators often, this is an immediate response function. That is, when you have a number on board, on the display, and you press this button, the calculator immediately performs that operation on the number that's on display. Now, this is what I got as a result. Now, when I say immediate response function, it is making the calculation right when you press that button, as opposed to here, where we had the square root of 5, we had to press enter to cause the calculator to make the calculation. A little bit different kind of protocol on the two different kinds of calculators. Well, it's pretty easy for us to identify the square roots of squares, especially if we're dealing with two-digit numbers. But if we're not dealing with squares, to check the reasonableness of answers in certain problems, it might be valuable for us to be able to make a pretty good estimate of the square roots of numbers. And that's not too difficult either if we realize what's being requested and some convenient square roots that are in the neighborhood of the value. Here's what I mean. If we're thinking about the square root of 50, you see, then we might think that, gee, 50 is near a square. 49 is a square. And since 50 is very near that square, the square root of 50 would be near the square root of 49. That's the kind of logic that we're using in this. Now, to be able to use that kind of idea, that kind of thought pattern, we need to be familiar with squares. You see, two-digit squares, and some of them are these. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. That's kind of far enough for us because I'm running out of room here. 11 squared is 121, 12 squared is 144. I think those are all important for us to realize. And what you do is this. You think, gee, the square root of 50, well, 50 is in the neighborhood of 49. We know the square root of 49 is 7. Okay, since 50 is a number a little bit bigger than 49, then its square root is going to be a little bit bigger than 7. So this is going to be approximately 7.1. And I'm just guessing here. You might check it on your calculator, but I'll bet this is pretty close, you see. Maybe it's 7.08 or something like that, or maybe it's 7.12, something like that. But to the nearest tenth, it's probably 7.1. Anyway, a similar idea on all of these. The square root of 97, well, 97 is in the neighborhood of 100, and we know that the square root of 100 would be 10. And since 97 is a little bit smaller than 100, then the square root of 97 would be a little bit smaller than the square root of 100. So this square root is a little bit smaller than 10. So maybe it's something like 9.8, you see. And here, the negative square root of 36. Well, I can just slide over with that negative business, you see. And I'm thinking in terms of 38, the square root of 38. So 38 is in the neighborhood of 36. And you see, you're looking over here. If you're not familiar with these, then you might make a list of them and just refer to them a little bit. And so we're thinking of, gee, 38 is near 36. The square root of 36 is near the square root of 36. So the square root of 38 is near 6, a little bit bigger than 6 because 38 is a little bit bigger than 36. And so we might think something like 6.1. So negative 6.1 would be a pretty good approximation or estimate of this. Same idea here, negative 23. 23 is in the neighborhood of 25. The square root of 25 is 5. 23 is a little smaller than 25. So the square root of 23 will be a little bit smaller than 5. And so this is roughly 4.8 or 4.9, something like that. Whoops, 8 or 9. I'm just about to make a mistake. And I think you probably see what that mistake is. It is that I didn't slide this negative sign over. That should probably be the first thing that we do in situations like this. Here we have the square root of 9 times 4, and we know that 9 times 4 is 36, and the square root of 36 is 6. But another technique to deal with this situation is like this, is to consider the 9 and the 4 as separate factors and as separate square root problems. That is, we can think of this as the square root of 9 times the square root of 4. The square root of 9 is 3, the square root of 4 is 2, 3 times 2 is 6, same result. This gives us a clue about a technique for simplifying situations where we're taking the square root of a number which is not a square. It turns out that we can simplify this a bit by identifying a square within that number and factoring it with a square times a leftover factor. So the square root of 50, we can factor 50 into 25 times 2. 25 is a square, so we take the square root of 25, the square root of 2 separately. The square root of 25 is 5, so we have 5 times the square root of 2. Now, generally, we won't write this step. We kind of understand what we're doing. Just looking at this, we're understanding that we're taking the square root of the factors separately, and so we have 5 the square root of 2. As an example, the square root of 18 would be the square root of, well, let's see, the largest square in 18 would be 9. So we have 9 times 2 for 18. The square root of the 9 would give 3, and the 2 is left under the radical. Now, for a number like 72, and when the numbers get large, there are some alternate ways of solving the problem. The easiest way is to find the largest square that's contained in the number. The largest square in 72 is 36. So we would factor this into 36 times 2, and then very easily we get 6 the square root of 2. But let's suppose that we don't see that 36 is the largest square in 72. And we might think just, very quickly when we look at the problem, oh, 9 is a square, and 9 is a factor of 72. So let's factor it that way. And let me show you how you would proceed through this and get the same result. You would think, oh, well, 72 is 9 times 8. All right, good. The square root of 9 is 3, so we have 3 the square root of 8. Oh, wait a second. 8 has a square in it, you see. It's 4. So this is 3 the square root of 4 times 2. Now, the 3 stays out here. The square root of the 4 gives a factor of 2 outside of the radical sign, and the 2 stays under the radical. So we have this. 3 times 2 is 6, so 6 the square root of 2. Now, sure, we went through a few more steps here, but we can go through these steps rather quickly. But the point is that even though you don't see the largest square in a number, all roads lead to Rome here, and you can often resolve the situation. There is a third way to work this problem, as a matter of fact. You could see that 4 is a square in 72, and factor 72 is 4 times 18. And then you would see the square in 18, and so on. Well, notice this, that we know the square root of 9 is 3, and we know that 9 can be written as 3 squared. And we know that the square root of the 9, that is 3 squared, is 3. And notice that if we write the 9 this way, that the square root of a number squared is giving us the number that we sort of start with in this squaring process. You see, and this gives us an idea of what we can do in other circumstances. If we can write a number as a value squared, then taking the square root of that situation allows us to sort of think of the squaring and the square rooting as offsetting one another. And so we can resolve the matter very quickly. I'm going to show you examples of that in a little bit. Now, do understand this, that the square root of 3 squared, 3 squared is 9, and that's why this works so nicely. But it's also the case that if we take this squared symbol, this exponent, and put it outside of the square root symbol, you see this is the square root of 3. And when we square the square root of 3, we also get 3. So we can think of the squaring and square rooting as it doesn't make any difference which one comes first, you see. And here it's kind of like implying that we're squaring the 3, and then after we do that, we're going to take the square root. Well, it doesn't make any difference because we can take the square root and then do the squaring, and it comes out the same in the wash. After all, this is a request for the number which when squared is 3, and we are squaring that number which when squared is 3, and therefore we do get 3. Okay. Let me show you some business on the 72. We already know what the square root of 72 is. We already simplified it a little bit earlier. But I want to go through a pattern here that will apply when the numbers get a little bit bigger. We could go through a thought process with something like 72 and say, well, I can't see the squares in here. I'd like to see the exponents on factors, like these exponents of 2. I know that I can, when I take the square root of a number squared, the result is the number. You see this being squared. So I'd like to see that, and so I can see that easily if I can perform a prime factorization. So I would go through and I'd say, all right, I want to perform a prime factorization of 72. And you start the prime factorization process by saying 72 can be written as 2 times 36. 2 is a prime number, you see. Now bring down the prime number and say, gee, what's the smallest prime number that goes into 36? Does 2 go into it? Yes, it does. So we can rewrite 36 as 2 times 18. And now bring these two down and think of 18. 18 is 2 times 9. And then for 9, does 2 go into 9? No, but 3 does. And so write 9 as 3 times 3. Now when we have a string of prime factors, this is a prime factorization, and we can consolidate matters by using exponents. Okay, so we could have then for the square root of 72, the square root of 2 cubed times 3 squared. Let's look at it like that. So the square root of 72 is the square root of 2 cubed times 3 squared. Now we think, let's sort of factor this so that we can see squares and leftovers. Now squares would be, in this situation, and we're talking about numbers that are squared, you see, that are indicated to be squared. So I'll factor 2 cubed as 2 squared times 2. And I'm putting the 2 squared here and the leftover 2 factor over here, and I'm bringing down this 3 squared. Now, the square root of I can take the square root of each of these separately, each of these 3 factors separately. Actually, there are more than 3 factors here, but I'm thinking of this as 3 factors. And so I can take the square root of 2 squared, the square root of 3 squared, the square root of 2. That's the way I'm thinking about it. The square root of 2 squared is 2, the square root of 3 squared is 3, and then I bring down the square root of 2. And then 2 times 3 is 6. So 6 the square root of